All right, back to the conservation of linear momentum. It's hard, but we can do it. All right, I'm just going to have to go in and out of the pirate here. I don't know if I can do it all pirate mode. Okay, so we have the conservation of linear momentum, and this is a recipe that's going to allow you to do this, okay? So the main equation is shown here. This is the conservation of linear momentum. It's actually 3 equations, so I'll just show it to you in the x direction and you'll get the idea for how you would do it in the y and the z directions. We have the sum of the forces and the control volume in the x direction for the x equation. And that we're going to rewrite this for what we call 1D inflows and outflows, where the velocity is not varying across the cross section, okay? So those end up looking like this. The summation of rho times the x velocity, and there's a sign here to get correct, plus or minus vx, and plus or minus q, okay? And basically you want to remember what that's talking about, right? It's talking about what we learned with the conservation of linear momentum. Basically says, if ever the force was to be had in any of the ever which ways, then say I, ye mangy old pirates, that momentum was definitely made. So, what does that mean? That means that if you exert a force on a control volume, and all the control volumes that we're going to be dealing with in this unit are going to be either stationary or moving at a constant velocity. If you exert a force on the control volume, then that means you must have created some momentum. And that right-hand side is the net momentum that is leaving the control volume. It's the net x momentum in the control volume, okay? So here's the recipe. And like the pipe flow recipe, this one really, you follow it, you can't go wrong, okay? So the first thing I would recommend doing, and you know, it's up to you, but I know some of you have a little bit of extra time on your hands right now. What you want to do is channel your inner pirate. So step -1 is basically to say, get yourself going with the pirate mode. Personally, I would recommend really getting into it. So that's better. Okay, now we're going to, oh, really you? Now we're going to go back to the worksheet. Okay, so check. We said R. Boy, I'm really kind of peppy here, being cooped up for days and weeks. Next one we're going to do is to draw the control volume in the coordinate system. Okay, so the example that we're going to be working on is on the back side of this handout here. This is the system that we're working on, okay? And we already have our axes drawn in here, so we have our x, y, and z. So z is in this direction, y is in that direction, x is in that direction. Now I'm just going to very clearly define my control volume. So I'm going to make it be this bend. So we have flow going in one side of the bend and going out the other side of the bend. So this will be the control volume, like that. And the flow is going in and out of the control volume here. I'm going to call this location 1 and location 2 just to make it straightforward, okay? So related to that is at these control sections, which are where the fluid is going in and out of the control volume, determine the velocities, flow rates, and pressures, okay? So for this particular example, you have pressurized water, and we are given the pressure at location, where is the pressure at this one? The pressure at the inlet is 200 kilopascals, and the pressure at the outlet is 155. So I'll call this one P1, and I will call this one P2. We have a velocity of 10 meters per second. The area of both of those cross sections is just 0.0095. So as usual, Q is equal to V bar times A, which is equal to 10 times 0.0095. And we can do that one in our head, and we get 0.095 meters cubed per second for the flow rate, okay? So we have our flow rates, we have our velocities, and we have our pressures, okay? So that's good. So sometimes you might need to use the pipe flow energy equation to get the pressures at one location or the other, and that would be plugged in at this step here, okay? So flow rates, velocities, and pressures. Got it? Now we're going to make a free body diagram for the control volume, breaking the forces into the X, Y, and Z components. So I think for the sake of simplicity for this example, I'm just going to focus on the X direction. Is it the X or which one am I doing? No, I'm going to do the Y direction because that's really where the action is for this problem. Okay? So if you look at this, you might think that you might have a bit of a recoil effect in the Y direction because you have fluid moving into the control volume and moving out. We're going to see that it's a little bit more complicated than that, and that's really why you want to stick to this recipe here, okay? But anyway, free body diagram is where you're going to draw on these different forces, and some of these forces are going to be a little bit new, so pay attention. So the first kind of force that you want to draw in is what we call a support force, and as I mentioned, we're only going to be dealing with problems where the control volume is not moving, and therefore there's usually some sort of a force holding the control volume in place. It might be with the fire hose, it might be a hand. If it's something like this pipe, it might be these flanges here, which are serving to anchor that bend in place, but there's some sort of a support force, okay? So I'm going to go ahead and draw that in. And what I would recommend doing is to draw that in the positive direction of whatever direction you're dealing with. So in this case, Y, I'm going to draw it as a positive Y. And I always call it uppercase T for some reason unbeknown to me. I can't actually remember why, but I always call them capital T. So this capital TY is what we call the support force. It's that force that is holding it in place, and at present we don't know that, okay? So we got the support force. Now we're going to do the weight, okay? And normally if we were doing this in the vertical direction, well, I guess we can go ahead and draw this in. So we would also have the weight, and the weight of the control volume would include the weight of the fluid and the weight of the pipe, okay? So that would be another force to draw in there. Stuffed animals, very funny. Gauge pressure force from any pressurized fluid outside of the control volume at the control surface acting back in on the fluid in the control volume. No pressure force if the pressure is 0, okay? So because locations number 1 and locations number 2 are pressurized, this is not a free jet at 1 and 2, there is actually going to be a pressure force at both of those locations from the fluid outside of the control volume acting back in on the fluid inside the control volume. So that pressure, you could think about the pressure distribution looking like this. This would be your P1. Think about that distribution acting back in on the fluid. And of course, we multiply by the area there. This one over here, even though the fluid is going out to the left, we are thinking about the pressure from the fluid outside the control volume acting back in on the control volume. And the pressure there would be P2, more or less uniform over the cross-section, okay? So the forces there are going to be not P1 and P2, but P1A1, I'll just write that in, and P2A2, okay? Those are forces from the fluid outside of the control volume acting back in on the control volume. If 1 and 2 were free jets, you wouldn't have those forces there, okay? So keep that in mind. But this, if it's a pressurized pipe and you sort of cut it where your control volume is, you have to have the pressure from the fluid outside exerted back in on the control volume, and we're working in gauge on this problem, okay? So that's a tricky one, and that will be important. What else? And that's it. So you might think, oh, what about this thrust force and things like that? Do not add that in as a force, okay? That sort of comes out of all this, okay? So just stick with me for a sec. So that was the left-hand side of the equation, okay? So the sum of the forces for this problem, we would, if we're doing this in the in the Y direction, I hope I didn't say X before. If we're doing this in the Y direction, the forces that we would add in, we have P1A1 in the positive Y. We have positive Ty because we've drawn it in the positive direction. And then we actually have positive P2A2 as the forces. And we're going to kind of add down. That's why I'm writing them in this way in a column. Okay? What else do we have? Okay, so that's it for the forces in the X direction. And you could do this also in the Y and the Z directions. Or sorry, Y direction. I'm sorry, I keep saying X instead of Y. It's usually X is the principal direction, but Y. Okay, so now we're going to do the fluxes, and this is the hard part, and this is the hard part where you have to pay attention. We're going to do the fluxes in the Y direction, and the flux of momentum in the Y direction, let's just change this to be Y, is rho plus or minus v sub y plus or minus q. And those are multiplied together. I write plus or minus to indicate that you need to get a sign in front of those right. Okay? So get your signs right. The velocity plus or minus v sub y gets a positive or negative sign depending on whether it is in the positive y or negative y direction. Whether it is in the positive y direction or minus y direction. Okay, so the velocity in that product, the sign will be positive if the velocity is moving in the positive direction and negative if it's moving in the negative direction. So over here we have the forces. The fluxes over here are going to be this rho plus or minus v sub y plus or minus for the sign q. And we're going to do this flux for cross-section number 1 and cross-section number 2. So for number 1 we have rho. We know we have rho for number 2. And the velocity at location 1 is 10 meters per second. That velocity is in the positive y direction. So I'm going to write that like this, positive 10, because that velocity is in the positive direction. Okay, remember that the fluid is moving in this way and moving out this way. Okay, the velocity for location 2 down here, this velocity here, this v2, which is the same as v1, the area is not changing. That one is going to be a negative 10 because it's in the negative y direction. Okay, so far we're trying to form these products of the rho VQs. Okay, all right, so that is how you get the sign right on the velocity. Now how do we get the sign right on the Q? Q gets a positive or negative sign depending on whether it is an inflow to the control volume or an outflow to the control volume. So if it's an outflow, you give it a positive sign, and if it's an inflow, you give it a negative sign. Okay, see, that's not that hard. Okay, so what does that mean? Why don't you do this one in your head? So for location number 1, is that an inflow to the control volume or an outflow? Yes, you over here. That's an inflow. That's good. Very, very correct. So we would have plus or minus Q. Let's try to get someone else to participate here. Yes, you over here. Okay, speak up. Yes, that's right. So what they said, I know it's hard for you guys in the back to hear there, but they said that that is an inflow and therefore it would have a negative Q. Okay, and we know our Q. I'm just going to write it as negative Q. How about somebody else? Somebody on the right side of the room. Yes, you. I'm sorry, I can't call on all of you. Yes, go ahead. Yes, that's right. Number 2 is an outflow. This fluid is leaving the control volume, and therefore the sign for that Q is a positive. Okay? That's correct. Okay, I'm sorry there are no more questions. Just put your hands down. Okay. Good. So we are making excellent progress. Okay, so that is the fluxes, and the fluxes is the right-hand side. These are the fluxes over here, and you're going to add them all up for every place that fluid is leaving or entering the control volume, and then over here we have the forces. Okay, so the forces and the fluxes. All right, so now the last thing is to add those together and set them equal to each other. Okay, and we are only doing this in one direction. We'll move on to 2 and 3 directions later. So what do I mean by that? So the reason that I wrote it like this is that I'm going to now do a summation adding downward so that the sum of the forces is equal to P1A1 plus that support force T sub y plus P2A2, and that is going to be equal to the sum of the fluxes, which is minus rho times 10 times Q. That's the first one. And actually the second one also has a negative sign, minus rho 10 Q. I just farmed out that negative sign, okay? And so this is our grand equation here for this problem. And what we can do now is solve for the thing we're looking for. And I forgot to actually show you what we're looking for. We're trying to figure out this support force. So what is the force to support the pipe bend given the below parameters, okay? So if we rearrange this, and let me just check my notes and make sure I didn't screw anything up here, we get that the different terms in this, if you want to follow through on your calculator just to check things, the pressures were in kilopascals, so you have to be a little bit careful when you multiply by the area. The units, incidentally, of all of these terms, if you use SI units, are newtons. So we would have newtons over here. A pressure times an area is a force. That's a newton. this force would end up in newtons. Over here, believe it or not, a rho VQ, if you have V in meters per second and Q in meters cubed per second and rho in kilogram per meter cubed, you would get newtons over here too. Okay, so if you plug everything in correctly, you would have newtons. One thing to note is that for the BG system, this would want to be slugs per foot cubed, not pounds per foot cubed. Okay. Anyway, so if you plug in the things for this different the different numbers that you're given, you have 1900 plus T sub y plus that P2A2, which is 1472.5. That is equal to minus 950, and actually the same, right? Minus 950. Okay. And what you get if you rearrange, and these are newtons, of course, and what you get if you rearrange that is that T sub y is equal to negative 5,270 newtons, okay? And that would be your answer for this problem, okay? So that is how you do a one-dimensional problem, and you're going to move on to do two-dimensional problems. I think for another problem, a good quiz problem would be if you had a vertical nozzle. So I think maybe I'll just sketch you that really quick so you can think about that a bit. Where would I do that? Let's just go over here. La la la, notes, grids. I guess we're in dark mode here because it's nighttime. Okay. So here is our contracting nozzle. This looks a lot like a problem that you might see for a quiz. So something like this, right? And again, you have to be thinking about the recipe. The recipe would tell you to, so we have some sort of a V2 there and a V1 going in there. And I think you have a flange here. A flange is a way that you join two sections of pipe together. It actually wraps around the whole pipe, but I'm just drawing it on the outsides. And I think for this one, you're trying to figure out the support force from the flange, okay? So I'll just get you started. I'm not gonna give you the whole problem, but the control volume we want to think about looks something like this. So you would have a control volume that includes the pipe, and because this is in the vertical direction, gravity acting downward, you're going to want to be sure to include the weight in your forces and fluxes, okay? So what you want to head towards is, again, your forces, and this would be, in this case, in the z direction, and we can take z positive upwards if we want. And the fluxes over here, I'm kind of making a smaller table than I would recommend for you. Those are the fluxes in the z, and separate them. They don't get along until you set them equal at the end. So for the forces, you want to be thinking, this one here is a free jet, so there's actually no need to consider the pressure from the fluid outside acting back in on the control volume. That doesn't actually, zero pressure basically. But up here, you would have a pressure, and that pressure would actually be acting like this on this face of the control volume. Don't forget to multiply by the area to get the force from that pressure. You mentioned the weight as well, and then there, this thing is not just sitting there magically. There's a force holding it in, and that would be a support force. And one question is, I don't know, for this problem, you might think, well, if it's super heavy, I might need to hold it up, right? In which case, the support force may need to be like that, right? And then you might think, Ian, your friend, might say, well, I actually think that this is, this V2 is going to have a huge recoil effect, and therefore I'm going to think that the TZ, the support force, should be down. And he might draw it like that, right? And the answer is you don't really know till you run the numbers. Like the last one we did, we didn't know the sign of that T sub y until the end. What I would say, I think it's easiest to always, if you don't know which direction it's going, or even always, just assume it's always in the positive z direction or the positive x direction, whatever you're working in. So in this case, positive z direction like that, okay? And let the signs work out from the math. If you were wrong, you'll get a negative tz, and you will know that it's actually acting in the downward direction, right? And if it's positive, you know that you guessed correctly, or in this case, it's in the positive direction, okay? But That is my advice for this support force. And again, the support force in this case is being provided by the flange here, okay? And you want to head towards the forces and the fluxes for this, okay? So just to sum very quickly, I know you guys are, I did look at the, what am I even doing here? I did look at the, this is the world's cheapest patch. I made it with some supplies for my daughter. I did look at the exams, and so far they looked really good. So I'm excited about your work on those, and I'm hoping that you can keep going with these lectures and stay engaged with the class. And I hope that you are finding ways to entertain yourself during these very sometimes boring times. But I wish that you are staying safe, and also that you work hard. We have 6 more weeks. Keep going. You can do it. There's a quiz on these 2 videos that you watched for this lesson, and I think you can do it after seeing this. So anyway, blah, blah, blah. I'm sure you're listening to a lot of blah, blah from your professors today, so I'll stop doing the blah, blah from this one. And those are my kids screaming in the background. And let's see if I can stop. See ya.